seems to me like a revolution going on here in creativity using computers. I'm going to tell you about what I think is a revolution going on in the way we collect data and the kinds of data we collect and how it's going to impact, quite frankly, all of your health. So this first slide really frames the problem as I like to think about it. Hopefully most of the time you're healthy, but there are times when you get sick, and sometimes that can be quite severe. And really, as a scientist, we like to think about these as states. So again, healthy state, hopefully most of the time, occasionally transitioning to disease states. And we know that these states are impacted by many things. One is your DNA, which you're born with. That, well, until recently, it's not something you change so much, but it's something you could change now, potentially. And then it's all these other things that influence your health as well. The so-called exposome is one way this is described. So it's like pathogens such as viruses you might get exposed to, the food you eat, stresses, exercise. We know intuitively these all impact our health. And I would argue as scientists and actually many clinicians, we want to understand this really in quantitative terms, because we're at the stage where right now you could actually get your genome sequenced, well not you, but genomes could get sequenced before kids are born, actually from DNA circulating in the mother. And then you'd like to know with particular sets of changes in those DNA relative to, say, a reference, what would be the impact of certain things. And as an example, if you're at risk for Parkinson's, you probably shouldn't be a pesticide worker, because that increases the probability with which you might get Parkinson's. So you might say you shouldn't be a pesticide worker anyway, and that's a different subject. But you especially shouldn't be one if you're at risk for Parkinson's. And I do think we're going to be entering this world. I don't know, how many of you have seen this movie, Gattaca? Okay, quite a few. So anyway, this is one of my favorite movies. You can buy for $5 at Walmart. And a lot of what I'm going to say, I think, actually is very much in that realm. So anyway, this is how we think about things. Now, there has been a revolution in our ability to collect information. One is you can actually get your genome sequenced. And in fact, I would argue there's been a revolution in 3 areas that are really impacting health, probably more, but 3 certainly that we work in that impacts health pretty dramatically. One is this DNA sequencing, where you can get your DNA sequenced now. The sequencing cost is less than $1,000. Actually, the interpretation to do it right costs many thousands of dollars. That's actually the bottleneck here. It's not the sequencing anymore. But all of you can get your genome sequenced. How many of you have had your DNA sequenced? Yeah, quite a few. This is amazing. This is Stanford here. Awesome. So, yeah, well, depending who would interpret it, you either got a good job or maybe not so good a job. So anyway, that's something we can talk about later. There's also been a revolution in these things called mass spectrometers. That's what shows up in airports, right, when you get screened for bombs and things. That's a simple mass spectrometer, but there are now very sophisticated ones. You can measure tens of thousands of molecules in your blood, in your urine, in your bodily fluids that let us actually follow our molecular composition, if you will, at a level that's never been possible. And then fairly recently, there's been this revolution in wearable devices. I'll talk a little bit about that as well. Together, these let us literally collect tons of measurements about ourselves now as they're being applied to healthcare. So just to give you one example, DNA sequencing is really transforming healthcare in many ways. You may know cancer is a genetic disease. There's always changes when cancer cells arise. And people are now turning to, in fact, I would argue anyone who gets cancer should have their DNA sequenced, the cancer cells, so that you can try and find variants that might be causing the cancer, and sometimes that's druggable. Okay, and that's what people are doing now. For certain cancers, it's pretty much state of the art, like lung cancer. There are 5 different drugs out there that work very, very differently. Depending what genetic change has, determines which drug you would use. So this is one area where genome sequencing can have a huge impact. Solving undiagnosed disease, about 0.4% of kids are born each year and they have a severe problem and they can't figure out what's wrong with them. We're turning to genome sequencing their DNA, and about a third of the time they can solve those cases. Not all the time, but a third of the time. Rarely is that actionable, meaning it doesn't lead to treatment, but sometimes it does, but it's still usually useful. I mentioned prenatal diagnostics. Nobody does amniocentesis anymore. They actually sequence the fetal DNA out of the pregnant mom. Okay, you can take the blood, and actually there's some fetal DNA floating around in there. You can sequence. That was actually pioneered here at Stanford by Steve Quicksaw, amongst others. One area that interests us a lot is this one. If you're healthy, is getting your genome sequence, is getting your DNA sequence useful. So your genome, I forgot to say, it's actually a collection of all your DNA. So anyway, this is what you can now do now, and this is an area that we work on a lot. We also call it personal genomics. So a number of years ago, we actually took advantage of all these technologies and started a project to actually study people in incredible detail. We did work on sequencing their DNA, but we also make all these other measurements. I won't have time to go into them, but we're basically making as many molecular measurements as possible in your blood and in your urine to see what it looks like. I'll explain more in a minute. What is your molecular composition when you're healthy and what happens when you transition to disease. So we basically follow all your modified DNA. You may have heard of the term epigenetics. We can measure that. We can follow all your RNA, your proteins, immune molecules, metabolites. We can follow pretty much, not everything, but quite a lot in your blood, again, and in your urine. You may have heard about the microbiome. These are the microbes. I don't know if you know, but you have 10 times as many cells in and on you that aren't you, that are you, meaning we're mostly ecosystems. Only a little bit of us is human. Most of us is bacteria, by about 10 times as many cells. And it's very, very important. It digests your food, makes essential vitamins. It's essential for us, actually. And so it's on our skin. Most of it's in our gut. And then we also, so we make all these measurements. We also bring in biosensors, and we follow people over time. That is, we sample them typically every 3 months when they're healthy. When an adverse event comes along, a viral infection, things like that, then we take many more samples. So why are we doing all this? Well, we're trying to, again, define what is health. What does it mean to be healthy? And how does that change amongst different people? We're all not the same. It turns out our baseline molecular composition is not the same. This is one of the things we're unraveling. We can tell age signatures. We can tell all kinds of things now. We do want to see how you change over time, meaning aging markers and other things that might change as you go through various infections and things. We're trying to understand how if I threw a virus on this room, say half of you would get sick, the other half might not. You'd have a lot of common symptoms like congestion and things, but some of you would get very sick and others maybe not so sick. So we have personal responses and we have common responses, and we're trying to figure all that out. And lastly, as we do all these molecular probings, we actually learn things that are very important for people's health. I'll show you a few examples in a bit. So we actually started this out, believe it or not, by studying me, actually. I was the guinea pig for this. I didn't know I'd be interesting. Turns out everybody's interesting with profiling. I'll show you some of that. Not just our mothers. We're all very interesting, scientifically. And we've been profiling me for 7.5 years now. And again, we basically sample roughly every 3 months when healthy, when a viral infections. I've been through 10 viral infections, 8 of them are shown here. These are all common viruses. That's a rhinovirus, most common cold out there, so on and so forth. So we have had Lyme disease, actually had a bike accident. I don't go looking for these things. If they do happen, I do collect more samples, and I figure I might as well get some good data out of an adverse. That's sort of how I do this. I've been doing all kinds of dietary studies. So we started actually by sequencing my DNA, and I won't spend a lot of time with this to predict a lot of what I know already, like high risk for heart disease. Everyone on my father's side, he had 9 brothers and sisters, they all died of a heart problem. High risk, high cholesterol, I knew that already. But there were some surprises. One is high risk for type 2 diabetes. That came out as the average male is expected, normally would have a 26% chance of getting diabetes in their lifetime. I was up to 47% based on my genome. So we can make these kinds of things. You can do this for hundreds of diseases. Again, most of mine match, but a few surprises. This one, again, was a big surprise. And it turns out, while I was during the course of the study, wouldn't you know it, I did get type 2 diabetes. It made a big splash at the time because the first time someone used their genome to predict risk for disease, and I got the disease. In my case, I actually caught it right after one of these nasty viral infections. It's called respiratory syncytial virus. It's common cold in kids, not so common in adults, does occur. And when adults get it, they get pretty sick. So what happened was shortly after I got it, my glucose spiked essentially quite high to the point where I was classified as diabetic. So it's arbitrary, but this is a measure of high sugar. It's called hemoglobin A1C. It's not that commonly measured. It should be measured in everybody. I'll bet a lot of you hate to say it. I guarantee a lot of you are pre-diabetic and have no idea of it. And probably some of you are diabetic and have no idea. So anyway, it's arbitrary, but when this number hits 6.5, you're classified as diabetic. And initially when I was measured, I was right on the edge at 6.4, and then 5 weeks later, it was higher and classified as diabetic. As I say, once I learned that, I had been biking. I doubled my. I live on Stanford campus, but it's a big campus on the other side. So I doubled my biking, started running, and gradually, it's about 8 months to bring it back under control. I also changed my diet a lot. So again, this made a big splash because using Genome to predict disease, in my case, got under control. Some people say, well, it might have gone away on its own, but we accidentally did the right control experiment here. These are the blips I showed you before. That's where the RSV infection occurred. That's hemoglobin A1C. That's fasting glucose. It turns out that I'd stopped running, and you'll see in a minute, we scaled the study. Now we studied 100 people, not just me. And that turns out to be a big project. And we were collecting all the data. It was a blind study, if you will. The data were coming in, and then nobody was looking at it until somebody looked at it here and said, Mike, your hemoglobin A1C is 7.0. You're diabetic again. So I had no idea. Sampled me a few times, started running. Basically got under control for a little bit, but not as far down. Got it to 5.7. And it was creeping up. This stopped about 2 years ago. It was creeping up to 6.4. So I changed my exercise. You can't tell, from running to weightlifting. Like I say, I know you can't tell that. But anyway, the point out of that is, and the reasons for doing that, I thought there's some literature that says muscle mass should control glucose, and that logic made sense to me. It actually failed miserably because my glucose shot up faster. So I'm back diabetic. So I'm working on diet to get down.
Are you saying that your virus, you think, triggered the diabetes, or
yeah, so that's
made you notice it?
That's the hypothesis. Well, in this case, we would argue triggered because it had been running along perfectly normal, and it was after the viral infection. So we think I'm genetically predisposed, and then in combination with this viral infection is what triggered the disease. And it turns out I have 2 brothers, 3 sisters. They all came to visit, so naturally I took blood from all them. So you got to watch if you come to my house. We did. It turns out they're thinner, the same build as me or thinner, and they're all pre-diabetic as well. They're ranging from 5'7" to 6'2". So there's no question we have this genetically running in our family. And so the hypothesis is that the genetics has us predisposed and the viral infection triggered it. And anecdotally, this is not real science, but anecdotally I can tell you there's been a lot of other people in similar situations. In fact, I literally got an email today from someone who had actually herpes simplex virus, and actually right after that got type 2 diabetes. So the viral infections have been associated with type 1, not type 2. So this is new territory. Nobody knows how type 2 comes on or how fast it comes on, and this sort of thing. So everybody assumes it's gradual, and I think for some people it is. So it's what we're trying to figure out from this 100 people we're studying. I'll tell you more about that in a minute. So as I say, we're now studying 100 people. We're doing everything to them that we do to me. About 60% of them are pre-diabetic, so they're at risk for type 2 diabetes, and some have converted to become diabetic during this time. And again, we're trying to see this. Nobody's actually had. It turns out people bounce around a lot in their sugar levels, and so and that is true for me now. I don't know about before, and so it's possible they're bouncing it in around, and then they get stabilized in a high glucose state. So that's something we're looking at. But anyway, several have converted that way, but again, we're sampling them every few months, and many times when they get a viral infection, stress, like 7 of our folks who had colonoscopies, we'll take a lot more samples then. And so on. And a lot of people are running through dietary perturbations. I won't have time to tell you about that. So what's special about our group is that they're actually making their data completely available to the scientific community, which is great, so that it can be very useful. There's a ton of stuff we've learned from the studies, and I'll just give you a few vignettes. I want to tell you about the wearable stuff we're doing. But one thing that's come up, oops, it's now 12, is people have said, well, Mike, yeah, you learned something about your genome, but what about most people? If I went out and sequenced all of you, how many of you would learn something useful? Most people say, well, it's really not that useful. You can't really learn it. So we actually tested that. We went out, of our 100 people, we've gone through 70 people's genomes in incredible detail, like mine, and 12, so there's a misprint, there are 2 now APCs. 12 of the 70, so 17%, have some mutation in their DNA they should know about that's actionable. And probably the most famous one, many of you may be familiar with, BRCA mutation, right? Angelina Jolie has a BRCA mutation. And so this puts, for women, at higher risk for for breast and ovarian cancer, for men, breast and prostate cancer. And actually, basically, women often do prophylactic surgery. Minimally, most people get checked and screened much more frequently when you have this mutation, which is what you should do at least. And so that's what's happening. This happens to be a male, and of course he has 2 sisters. And there's a question of what do you do about relaying that information. All of these things though put people at risk for cancer. This individual actually has a mutation that makes him predisposed for a heart problem, and it turns out we actually did something called a stress echo, and he has a heart problem, actually. So he's on drugs, which we uncovered essentially through his DNA. A few of our folks in the study are diabetic. This person was thought to be type 2 diabetic. Turns out they have a genetic mutation, it's called a MODY mutation, that makes them predisposed for diabetes. It's completely different from type 2 diabetes though. So the way they were classified was all wrong, and the drugs used for treating them is very, very different. In fact, there's a famous story of a type 1 diabetic who sort of late in life actually got his DNA examined, and he had one of these MODY mutations. Type 1, people take insulin injections. He had taken insulin injections his entire life, 21,000 injections. He would have needed a total of 0 had they sequenced his DNA way back at the beginning, because they would have put him on a different drug, and it would have been totally different. So this is some of the power you can gain from this. So it's not the majority of people who are helped by this, but if you're one of these 12 people, it's a big deal. It does affect what will happen when you go to the doctor. We'll do simple little screens like for this SHTB and this sort of thing to see if you have are actually developing this cancer. We've also learned things from other parts of the study. So I'm running out of time, so I won't spend the time, but we actually caught one person who had early lymphoma, another person with a pre-cancer condition, another person with a heart problem, as we profile people through this time, because we're looking at people in incredible detail. When you go to a doctor now, they measure 15 things. We're measuring billions of things, and that's the difference. And we're measuring it very frequently and over time, so we are catching these things they may not see. All right, I wanted to tell you, so that's these deep profiles, but we're also exploring this area about wearables, right? So how many of you are wearing a wearable right now? Okay, only a few. More of you had your genome sequenced and are wearing a wearable. That's amazing. I've never seen that before. So there's now about 1,000 of these devices on the market, actually. And about 4 years ago, we went through and started looking at these to see which ones would be most useful. Tested about 30 of them. Ultimately settled on 2 for our entire cohort of 100 people. But I actually wear now 9 of these devices every day. You might notice 3 smartwatches. This ring is not a secret society ring. It's an actual sensor. I can tell you what the radiation level is here. I think it's usually about 3 milligrams per hour. Yep, it is. So on and so forth. So we can make lots of measurements, heart rate, skin temperature, blood stress responses, your blood oxygen, so on and so forth. You can measure all these different things with these different devices. Some devices measure many things. And most of them relay information into your smartphone. So it all gets collected here, all Bluetoothed off, if you will, and collected there where we're trying to organize it. So let me show you some of the things you can learn from this. This is actually my profile. This first stuff's dead obvious. It's a no-brainer. This is my sleep pattern, heart rate, and skin temperature. So I sleep at night. It's high at night. There's a 24-hour clock here. Don't sleep during the day, except occasional nap there. Back to sleep at night. It's my heart rate, low at night, high during the day, back to low. Skin temperature, which is different from core temperature. High at night, goes low, high at night. Turns out, we measured this now, many people, there's 43 people, everybody's different. We all have different baseline heart rates, blood oxygen, skin temperature, et cetera, so we're all different, we have different baselines. So what do we do with that? Well, we also can see different activity patterns on people, and we can calibrate relative to that. And then we start looking for changes relative to your baseline. That's the power of this. We want to know what your individual healthy state is, and what happens when you deviate from that. Turns out this is one of my biggest deviations. It turns out on airline flights, your blood oxygen drops. This is known in the literature. Most people do not know this, including me before the study. But it turns out, it is in the literature. This is one short flight. His altitude, the plane goes up, comes back down. There's my blood oxygen. Starts here, drops down. They pressurized cabins to 8,000 feet. Blood would come back down, goes back up. That's a short flight. What's not clear from the literature is how low it goes and how long it's low. Well, it turns out most of the flight, it'll be 96% or low, and 5% of the flight will be 90 or below. We actually now think this is an underestimate. We're measuring more carefully. So this 96 number is important for something I'll tell you in a minute. So most of the flight, the plane goes up high enough, your blood oxygen, normally for me it drops to 94 or lower. Okay? So why is this important? Well, it turns out that it's associated with fatigue. That is to say, are we running out of time? Sort of, okay. All right, so for me, you can do these blind tests, and blue means I'm tired, red means I'm alert. And generally, when I'm 96 or below, I'm tired, or 96 or above, I'm alert. So 96 is sort of my threshold. And that's true in the plane, this is on the ground. You do these reaction time tests to see, your faster reaction time when your blood oxygen is high, and you're slower when it's low. So that's what this says here. So the bottom line is that your blood oxygen correlates with fatigue. So we think the reason you're tired on airplanes isn't because you've been working too hard, because you've been drinking too much late at night. It's because the air cabin pressure is low, and it's dropping your blood oxygen. Okay, so if you're a workaholic, this is really disappointing news, and I'm a workaholic, so this is extremely disappointing. But there's some hope. Oh, sorry, I forgot to say, I guess I took that out. It turns out, for me, for flights that are over 7 hours, you adapt, actually, so your blood oxygen goes back up. I don't know how true that is for others, but so if you're having trouble at the beginning of the flight, hang in there. There's hope. All right, so why is this useful? Well, we're collecting everybody's baseline measurements, and then we're looking again for changes from baseline. So this is a case where I actually figured, I'll get to the punchline, I actually figured out I had Lyme disease first from my wearables. So the backstory on this is I was in Massachusetts helping my brother put up fences for one day, where 55% of ticks are Lyme infested. 2 weeks later, I'm flying to Norway through Frankfurt. So that last flight from Frankfurt to Oslo, it's a short flight, and because I measure myself all the time, I knew what my blood oxygen should look like. It should look like this is a summary of all these green lines are my short flights. On this particular flight, my blood oxygen was 90 instead of 96 or whatever the normal is there. And when I landed, it stayed at 95. It never came back to normal. So it was low. So I also looked at my heart rate. It turns out that that was elevated. You can measure this several ways. And I later learned my skin temperature was up. So I knew something wasn't right, again, because I measure myself a lot. It wasn't jet lag. I've taken a lot of flights. It's very different. So then I got a low-grade fever. I went to a doctor in Norway who took my blood and said, yes, your monocytes are up. You have a bacterial infection. I think you should take penicillin. And I said, no, I think I should take doxycycline, which is what you use for Lyme disease. Now, as you might imagine, that was actually rather tense. Doctors don't like to be told by their patients what they're supposed to be doing. So he was very reluctant, but he gradually gave in. I'd warned him ahead of time it might be Lyme because of the whole timing. Anyway, he gave in, and then 24 hours later I cleared up. When I got back, I tested, and sure enough, I was positive for Lyme. I have the perfect control because before I left, I had given blood, and I was negative. So, in fact, I seroconverted during this time. There's no question, it's not a false positive, etc. We have all the right controls because I measure myself all the time. So, again, the first clue then for all this was my wearables that tipped me off something wasn't right. So that prompted us to look at, I've been wearing these devices for 4 years now. So looking over the 2 years of data we had at the time, it turns out there were 4 periods where my heart rate and skin temperature were up. One was a Lyme period. Each of these is a different day. You can see you can't miss those signals. They're blazing. But it turns out 2 days when I had viral infections, this one here and this one here, I also had high heart rate and skin temperature, okay, which made sense. But there's also even a 4th time where I had high heart rate and skin temperature, and I went back and looked at something called CRP. It's when you get sick, your CRP levels go up. And it turns out my CRP level is just as high as a viral infection and the Lyme disease. So in fact, I was sick, I didn't even know it. So every time I was sick, we picked it up with a wearable device. That prompted us to write this in a more high-resolution fashion, where we think with a short window, say, now we think it's 30 minutes, but for 2 hours for sure, with 0 false positive, or very little, we think that basically we can tell you when you're getting sick before you know it. We look for an elevated heart rate from your resting one before that's up over your background, again with a very low false discovery rate. This is a complicated way of showing it, but every one of these dots, it's a change when your heart rate goes up, and that's when it was reported, usually 30 hours later. So again, we think we can tell when you're getting sick from your smartwatch before you know it. So we're trying to actually roll this algorithm out. We're going to enlarge the study. You guys just going to roll it in once we get it going. We have to get all IRB approval and such. And that's the goal. Initially, we're going to see how often we're right. And then later, I want this orange light to go off on your iPhone whenever you're getting sick and you're not watching a scary movie or running or something like that. And you'll tell us how often we got it right. That's the goal. Why is this useful? Well, for those of you who have kids or have elderly parents, we think this would be really valuable for following them, right, remotely. My mom lives 3,000 miles away, and I can now tell, I think, when she gets sick, if I get this on her. She's 89, I want to know what's going on. So this is the kind of stuff we're doing. I won't get into this, but we also think we can tell when people are getting diabetes now from a smartwatch before they're getting sick. At least some signs of this is not as far along, but that's the goal. There's some additional measurements and so on. So I think I have to wrap here. Bottom line is we think your smartphone will be your command center for the future. We think you can all relay to your physician, not that they'll know what to do with it, but we'll try and tell them what to do with it. That will be the future, because what you get measured in a doctor's office is not nearly as accurate as what you measure from your smartwatch, we believe. And I'll just skip over that. We have an amazing lab. They actually work right upstairs here and over at our Genome Center. You can get tours if you're ever interested. And then lastly, here's a thanks to Shao, Jesse, and Dennis who led this. And here's a shameless plug for a book we had come out. I did bring a few copies if you're interested. So, thank you.